likes writing repetitive boilerplate code? Nobody does. And that's why in Swift 5.9 we are introducing Swift macros. Swift macros allow you to generate that repetitive code at compile time, making your app's codebases more expressive and easier to read. My name is Alex Hoppen, and today I'm going to show you how you can write your own macros. I will start off by giving you a short overview of how macros work. Afterwards, we will jump straight into Xcode and see how you can create your first macro. Having seen our first macro in Xcode, we will explore more roles in which you can use macros. And I will show you how I use macros to simplify the codebase of an app I'm currently working on. Finally, I will show you how macros can communicate errors or warnings back to the compiler, if they are not applicable in a certain context. So let's get started. Here we have a list of calculations that first-year students can use to practice their arithmetic skills. We have the result as an integer on the left, and the calculation as a string literal on the right side of the tuple. Notice how this is repetitive, redundant, and even error-prone, because nobody can guarantee that the result actually matches the calculation. Luckily, with Swift 5.9, we can define a stringify macro to simplify this. This macro also happens to be the one that is included in Xcode's template. The stringify macro only takes the calculation as a single parameter. At compile time, it expands to the tuple that we saw before, guaranteeing that the calculation and the result match. So how does this work? Let's take a look at the definition of the macro itself. Notice that it looks a lot like a function call. The stringify macro takes an integer as the input parameter and outputs a tuple containing the result, an integer, and the calculation, a string. If the arguments of the macro expression don't match the macro's parameters, or don't type check by themselves, the compiler will emit an error without applying the macro expansion. For example, if I pass a string literal to this macro, the compiler complains that string is not convertible to the expected argument type int. This is different to, for example, C macros, which are evaluated at the preprocessor stage, before type checking. But it allows us to use all the powers that you know and love from Swift functions, like being able to make your macro generic. Also note that this macro is declared with the freestanding expression macro role. This means that you can use the macro wherever you can use an expression, and that it will be indicated by the hash character, like we see with hash stringify. Other kinds of macros are attached macros that can augment declarations. I will cover those later. After checking that all the arguments match the macro's parameters, the compiler performs the macro expansion. To see how that works, let's focus on a single macro expression. To perform the expansion, each macro defines its implementation in a compiler plugin. The compiler will send the source code of the entire macro expression to that plugin. The first thing that the macro plugin does is to pass the source code of the macro into a Swift syntax tree. This tree is a source-accurate, structural representation of the macro, and it will be the basis on which the macro operates. For example, our stringify macro is represented in the tree as a macro expansion expression node. That expression has the macro name stringify, and it takes a single argument, which is the infix operator plus, applied to 2 and 3. What's really powerful about Swift macros is that the macros implementation is itself a program written in Swift, and it can perform any transformation to the syntax tree at once. In our case, it generates a tuple, like we saw before. It will then serialize the generated syntax tree into source code again and send it to the compiler, which will replace the macro expression by the expanded code. That's really cool, But now, I want to understand how all of this actually looks like in code. The new macro template in Xcode defines the stringify macro that we've just seen. Let us walk through that template and explore the macro's definition, how the expansion works, and how the macro can be tested. To create the template, I click File, New, Package. And now, I select the Swift macro template. Let's call our first macro WWDC. So what do we get with the template? Here, we have an invocation of the stringify macro, similar to what we have seen before. It takes the parameter a plus b and returns the result, as well as the code that produced it. If I want to know what the macro expands to, I can right-click on it and select Expand Macro. That's exactly what we saw before. But how is the macro defined? Let's jump to its definition. Here, we have a slightly generalized version of our previous stringify macro. Instead of taking an integer, this macro is generic and can receive any type t. The macro is declared as an external macro. This tells the compiler that to perform the expansion, it needs to look at the stringify macro type in the WWDC macros module. How is that type defined? Let's take a closer look at it. Because stringify is declared as a freestanding expression macro, the stringify macro type needs to conform to the expression macro protocol. This protocol has a single requirement: the expansion function. It takes the syntax tree of the macro expression itself, as well as a context that can be used to communicate with the compiler. The expansion function then returns the rewritten expression syntax. What does it do in the implementation? At first, it retrieves the single argument to the macro expression. It knows that this argument exists because stringify is declared as taking a single parameter, and all arguments need to type check before the macro expansion can be applied. It then uses string interpolation to create the syntax tree of a tuple. The first element is the argument itself, and the second is a string literal containing the source code of the argument. Notice that the function is not returning a string here. It is returning an expression syntax. The macro will automatically invoke the Swift parser to transform this literal into a syntax tree. And because it is using the literal interpolation style for the second argument, we'll also make sure that the literal's contents are properly escaped. Nobody likes bugs. But what I like even less are bugs in code that I don't see, unless I explicitly ask for it by expanding the macro. That is why you want to make sure that your macro is well tested. Because macros don't have side effects, and the source code of syntax trees is easy to compare, a great way to test them is to write unit tests. The macro template already comes with one. This test case uses the assert macro expansion function from the Swift syntax package to verify that the stringify macro expands correctly. It takes the stringify a plus b expression that we saw before as input and asserts that after the macro is expanded, it produces a tuple containing a plus b and the string literal a plus b. To tell the test case how to expand the macros, it passes the test macros parameter, which specifies that the macro stringify should be expanded using the stringify macro type. Let's run the tests in the same way that you might already run the tests of your app, to see if they indeed pass. The tests pass, And with that, we already have our first macro. In it, we saw its basic building blocks. The macro declaration defines the macro signature. It also declares the macro roles. The compiler plugin performs the expansion. It is a program that is itself written in Swift and operates on Swift syntax trees. We also saw that macros are very testable, because they are deterministic transformations of syntax trees. And the source code of syntax trees is easy to compare. So you might wonder, in which other situations can we use macros? We have already seen a freestanding expression macro. Just to recap, this macro is spelled with a hash and allows you to rewrite the entire macro expression. There's also a freestanding declaration role that expands to a declaration instead of an expression. The other kinds of macros are attached macros. These are spelled with an at, just like attributes, and allow the macro to augment the declaration they are attached to. For example, an attached member macro adds new members to the type it is attached to. To learn more about these other roles, I highly recommend watching Expand on Swift Macros, where Becca goes over them in great detail. But I want to focus on the attached member role, because it helped me improve the codebase of an app I'm currently working on. I'm also a ski instructor, and recently I've been working on an app that allows me to plan the tours I want to take my students on. One thing you absolutely want to avoid as a ski instructor is to take beginners on slopes that are too hard for them. I want to use the Swift type system to enforce that. That's why, in addition to the slope enum that contains all slopes in my favorite ski resort, I also have an easy slope type that only contains slopes suitable for beginners. It has an initializer to convert a slope to an easy slope if the slope is indeed easy, and a computed property to convert an easy slope back to a general slope. While this provides great type safety, it is really repetitive. If I want to add an easy slope, I need to add it to slope, easy slope, the initializer, and the computed property. Let's see if we can improve things using a macro. What we want to do is to automatically generate the initializer and the computed property. How can we do this? Both the initializer and the computed property are members of the easy slope type. So we need to declare an attached member macro. Next, we will create the compiler plugin that contains the macros implementation. To make sure that our macro behaves as expected, we want to develop it in a test-driven way. Thus, we will leave its implementation empty until we write a test case for it. After we define the macro's behavior in a test case, we will write the implementation to match that test case. And finally, we will integrate the new macro into my app. If all goes well, we will be able to remove the initializer and have the macro generated for us. To develop the macro, we work with a template that we created earlier. And since I don't really need the stringify macro in my app, I have already removed it. I start by declaring a new attached member macro using the @attachedMember attribute. I call it slope subset because easy slope is a subset of slope. The macro also defines the names of the members it introduces. In this demo, I will just be showing you how to generate the initializer. Generating the computed property is very similar, because it's also just a switch statement that switches over all the cases. With this declaration, we have defined the macro, but we have not implemented the expansion that it actually performs. For this, our macro references the slope subset macro type in the WWDC macros module. Let us go and create that type so that we can continue to the really exciting part, the actual macro implementation. Since we declared slope subset as an attached member macro, the corresponding implementation needs to conform to the member macro protocol. This protocol has a single requirement: the expansion functions, similar to expression macro. The expansion function takes the attribute with which we apply the macro to a declaration, as well as the declaration that the macro is being applied to. In our case, this will be the easy slope enum declaration. The macro then returns the list of all the new members it wants to add to that declaration. I know that it's very tempting to start implementing this transformation straight away, but we agreed that we wanted to start by writing a test case for it. So for now, let us just return an empty array, indicating that no new members should be added. Finally, we need to make slope subset visible to the compiler. For this, I added to the providing macros property down here. Before diving any deeper, I want to make sure that what we have so far works. While I could try applying the macro in Xcode and looking at the expanded code, I much prefer to write a test case for it that I can rerun whenever I'm making changes to the macro, to make sure I'm not introducing regressions. Just like in the test case in the template, we use the assert macro expansion function to verify our macro's behavior. What we want to test is what the macro generates when applied to the easy slope type. So we use that as our test case's input. And since the macro is not doing anything yet, we just expect it to remove the attribute and not add any new members. So the expected expanded code is the same as the input, just without add slope subset. Finally, we need to let the test case know that it should expand the macro slope subset using the slope subset macro implementation. For that, we need to map the macro name to its implementing type in the test macros dictionary and pass that dictionary to the assertion function. Let's run our tests now to check that what we have written so far actually works. It does. Great. But what we really wanted is to check that our macro actually generates the initializer, not just remove the attribute. So I'll copy the code that I previously wrote by hand into the test case, because really, that's what we want the plugin to generate. If we run the test again, it fails, because our macro doesn't actually generate the initializer yet. Let's change that now. The initializer switches over all the enum elements declared in the easy slopes enum. So the first thing that we need to do is to retrieve these enum elements from the declaration. Since enum elements can only be declared inside enum declarations, we start by casting declaration to an enum declaration. If the macro is attached to a type that is not an enum, we should be emitting an error. I added a to do so that we don't forget to do it later, and return an empty array for now. Next, we need to get all the elements that the enum declares. To figure out how to do that, I want to inspect the syntactic structure of our enum in the Swift syntax tree. Since the macros implementation is just an ordinary Swift program, I can use all the tools that you know from Xcode to debug your programs. For example, I can set a breakpoint inside the expansion function and run the test cases to hit that breakpoint. We now have the debugger paused inside the macros implementation. And enumDecl is the easy slopes enum. We can print it in the debugger by typing po enumDecl. Let's inspect the output. The innermost nodes of the syntax tree represent the enum elements, the beginner's paradise and the practice run slopes. To retrieve them, we need to follow the structure that is outlined to us in the syntax tree. Let us walk through that structure step by step and write the access code as we go. The enum declaration has a child called member block. This member block contains both the braces and the actual members. So to access the members, we start with enumDecl.memberBlock.members. These members contain the actual declaration, as well as an optional semicolon. We are interested in the declarations. In particular, those declarations that actually declare enum cases. I'm using compact map to get a list of all the member declarations that are enum cases. Each case declaration can declare multiple elements. This is because instead of declaring each slope on a new line after a separate case keyword, I could have written them on the same line as case beginner's paradise, practice run. To retrieve all of them, we can use flatmap. And now that we have retrieved all the elements, we can start constructing the initializer that we actually want to add to EasySlope. The initializer declaration has a single item, a switch expression. The switch expression contains a case for each element in the enum, as well as a default case that returns nil. We need to create syntax nodes for all of these. Two great ways of finding the syntax nodes to create are either by printing the syntax tree like we did before, or by reading Swift Syntax's documentation. We start by constructing an initializer Decl syntax. This type can be constructed by building the body using a result builder and specifying the header, that is, the init keyword and all the parameters. This will allow us to use a for loop inside the result builder to iterate over all the elements. Exactly what we need. I just copy the init header from our test case. Inside the body, we need a switch expression. This type also has an initializer that takes a header and a result builder. Let's use it again. Now we can use the power of result builders by iterating over all the elements that we gathered earlier. For each element, we want to create a new case item, which we can construct using string interpolation, just like we saw for stringify. We also need to add a default case that returns nil. And finally, we can return the initializer. Let's run the tests to see if we're indeed generating the correct initializer. We are. So we know that our macro works. And we can start using it in my app. To add our macro package to my Xcode project, I can right-click on it and select Add Package Dependencies. I can now select the local package that we just created. To be able to use the macro, I add the WWDC target as a dependency of my app. We can now import the WWDC module from the package and apply the slope subset macro to the easy slope type. If we build, the compiler complains that the handwritten initializer is an invalid redeclaration. And that's because the macro now generates it for us. So we can just delete it. It's always fun to delete code, right? So if we want to see what the macro actually generated, we can right-click on slope subset and click Expand Macro. And if I forgot what the macro does, I can also option-click on it to read its documentation. The next step would be to also generate the computed property. But I'll do that later today. By using macros, we were able to get the type safety of easy slopes without the need to write repetitive code. How did we do that? We started with the Swift macro package template. To explore the syntax tree structure, we stopped the macro's execution and printed the syntax node inside the debugger. This allowed us to see which properties we needed to access to get all the enum elements. And it was really easy to develop the macro on its own using a test case. After we added it to my app, it worked straight away. But what happens if your macro is used in situations that it doesn't support? Just like you never want to take a beginner skier onto a difficult slope, you never want to let your macro perform unexpected expansions or generate code that does not compile. If your macro is used in ways that it doesn't support, always emit error messages that inform your adopters about what's going wrong, instead of having them read the generated code to debug your macro. In that spirit, let's go and fix the to-do we left in our codebase. When slope subset is applied to a type that is not an enum, the macro should emit an error, saying that it is only applicable to enums. Just like before, let's start by adding a test case. This time, we are applying the slope subset macro to a struct. Since there are no enum elements in the struct, we don't expect the macro to generate an initializer. Instead, it should emit a diagnostic, that is, an error, informing us that slope subset can only be applied to an enum. If we run this test, it fails, because we are not outputting the error message yet. Let's go to the compiler plugin to do so now. Macro errors can be represented by any type that conforms to the Swift error protocol. I use an enum with a single case to describe the error message if slope subset is applied to a type that is not an enum. If we throw the error from the expansion function, it will be shown at the attribute that causes the macro expansion. If you want to show the error message at a different location than the attribute, generate warnings, or even show fixed states in Xcode, there's an add diagnostic method on the context parameter that allows you to generate rich diagnostics. But I think in this case, it's sufficient to just show a simple error message at the attribute. Now, let's see if we did everything right and if our tests pass. Great, they do. So how does it look like in Xcode if I apply slope subset to a struct? For this, let me copy the test case into a file. Xcode shows the custom error message in line with all the other compilation errors. That makes it easy for adopters of my macro to see what they are doing wrong. And you know what? Now that we have good error handling, I think this macro might also be useful for other developers specifying enum subsets, not just for slopes. Let's go and generalize it. To specify the superset of the enum that we have so far hard-coded as slope, we add a generic parameter to the macro declaration. And since the macro is now no longer specific to slopes, let's rename it to enum subset by right-clicking on slope subset and selecting refactor rename. I can also choose to rename all occurrences inside string literals and comments by command-clicking them. We now need to adjust our macro implementation to use the generic parameter, instead of the hard-coded slopes type. If we print the attribute inside the debugger and inspect its layout, just like we did for enumDecl, we can see that we can retrieve the generic parameter by accessing the argument type of the first argument in the generic argument clause of the attribute's name. So now that we've retrieved the generic parameter, we can replace the so far hard-coded slope type by the variable superset type. I still need to make a couple more changes, like renaming the initializer's parameter, changing the macro's implementation type name, and updating the documentation. I'll do that later. Instead, for now, let's make sure that our tests are still passing. Since we made enum subset generic, we need to explicitly specify that EasySlope is a subset of slope by passing slope as a generic parameter to the enum subset macro. Let's see if the tests are now passing. They are. I should really consider publishing this macro to others as a Swift package. So that's a lot of ground we cover today. Let's recap what we went through. To create a macro, you can start with the macro package template, which includes the stringify macro as a great starting point. While developing your macro, we highly encourage you to write test cases to make sure that the code your macro generates is indeed valid. And if you're doing this, you can inspect the layout of the syntax tree by setting a breakpoint in the expansion function, running your test, and printing the syntax tree in the debugger. And finally, if your macro is not applicable in certain circumstances, you should always emit custom error messages, so that even if things go wrong, your macro will shine. Thanks for watching, and I'm thrilled to see what kind of macros you will create.